faith that a lot of people have is that we will be able to explain everything in a rational way. I'm not so sure that's right when it gets too complicated. Then there's openings for all sorts of things. I flunked out of MIT. I had a love affair, which was very important to me. That was more important than anything I was doing in school or anything like that. And so I said, the hell with it. If you have a good idea, talk it up at colloquia, write papers about it. And very often you will find that there is a group that will condense under that idea. That's the first. There has to be some group that thinks this is worthwhile. And generally, I think that the grander the idea, the more likely is you will collect colleagues.
In 1916, Einstein predicted the existence of gravitational waves. However, it took almost a century for researchers to detect them. In this episode of the 632 Nanometer podcast, the team has a fireside chat with Rainer Weiss, the man behind the Laser Interferometer Gravitational-wave Observatory and winner of the Nobel Prize in Physics for the observation of gravitational waves. What are gravitational waves? Where do they come from? And why are they so difficult to detect? What detection approaches were considered, and how did they eventually succeed? In this podcast, you will find the answers to these questions and hear many other insights from Rainer Weiss about science and life in general.
Professor Weiss, could you explain us more about the physics of these space-time waves?
Suppose you've drawn a circle in space. In the X and Y plane, that circle oscillates from being an ellipse in one, let's say, with a long axis in the X direction, to a circle for a moment, and then into a long axis in the X direction. And then it keeps doing this back and forth and back and forth. And the technique for detecting it, these waves, is exactly that distortion. It's this, that you actually measure that distortion. And that sounds fairly simple. And the idea is fairly simple. But the trouble is, and here's the real reason why people have spent so many years arguing about gravitational waves and also trying to detect. And we're not the first people at by any means that tried to do that. That has a very complicated history. Ask me about that. But the thing that makes it very difficult is how stiff space is. Space does not like to distort. And I'll give you a way of saying it. Those of you who know a little about material science might know what the Young's modulus of a material is. I hope you some of you remember that. The Young's modulus is the stiffness, effectively, of something to distort. When you talk about a change in distance in a material divided by the separation, 2 points you look at in material. That's the separation. And then you say, how much does that separation change when you squeeze the thing with actual force? When you squeeze it with your hand, squeeze it. It turns out that squeeze is the amount of distortion, the change in position divided by the position. That's called the strain. That strain is proportional to the amount that you squeeze. And the proportionality constant is 1 over Young's modulus. Okay. So I'll give you some examples. I would talk in CGS units that we don't teach in. Okay. But it is necessary for physicists to talk about. And the thing is that if you want to, when you want to take a piece of steel and you want to know, you want to squeeze the steel, how much does the steel change its dimension per length for a given squeeze? So it turns out that Young's modulus is about 10 to the 12, okay, in units of dynes per centimeter square. They cause hardly any distortion in space. I'll give you the numbers in a minute. Hardly any distortion has been caused. The energy to make those distortions, even though they're tiny, is gigantic. And that's another way of saying space just does not like to get distorted. So now let me give you the number that is the number that we first measured. When we measured a gravitational wave, we measured a strain. That's a delta L divided by L of 10 to the minus 21. And in the early days of the field, Einstein, and it's a very nice thing to go look this paper up. It's a wonderful paper. Einstein wrote a paper in 1916, which is on the web. And you can read the paper in English if you want. It's also translated from German, so you have a German too, if you like. And Einstein makes a little mistake in there, which is not important. But he, in the end of the paper, even though he made the mistake, says, if you put all the numbers together that I have just presented, And that has to do with the things I just talked about. And you find out that this is impossible to measure. Nobody will ever measure gravitation. It will never play a role in physics at all. Let me give you some examples so you have an idea why he felt that way. And I've asked the people who own the Einstein papers, both in Jerusalem and that was for a long time at Princeton, how did Einstein do this? How did he come up with the fact that it's just impossible? He must have made some numbers like we do nowadays on the back of an envelope. And I've asked them to go find the envelope, but they haven't found it yet. Okay. It doesn't come with the paper. 1916 paper just says it's never going to be measured. It's hopeless. And here I did it for Einstein, so you can get an idea. They take two trains. Einstein must have known about trains, and they're not going very differently now than they did then. Maybe a factor too fast. Okay, but the United States trains are so slow that Europeans won't have anything to do with trains in the United States. We're way backward in the United States on train. Anyway, you take two trains in the United States, smash them together, and go take that smashing them together and make sure that you can get an idea how far you have to be away from it. How much does it take to crumple the train up? It might take several seconds. But so you go out some distance away from the system, and if you have to go at least 300 kilometers away from where the train's cracked so that you're in the radiation zone. And the strain that has been formed, the strain that you measure at that distance, some 300 kilometers away from where the trains collided, is 10 to the minus 45. Okay. Really tiny, almost impossible to dream of such a. So Einstein looked at that and he probably said, oh my God, this is never going to do anything. So then he might have turned to one other place where he probably could measure. He thought people could measure something like this. And that is looking at binary stars. Binary stars existed when he was thinking about this. And in 1916, 1918, people knew about them, but they didn't know of any fast ones. They just knew ones that took 8 hours, 10 hours to go around each other. Those are very fast. And those, he said, maybe an astronomer can see the loss of energy to gravitational waves in a binary stellar system. And when you make the number for that, for the kinds of things like a mass of a sun and something which has a period of tens of hours, you wind up with a strain that is about 10 to the minus 21. And you wind up with a change of if you looked at that system and you want to see the two stars getting closer together because they've lost energy, you would have to wait something like 10 to the 10 years to see anything. So it turns out Einstein must have decided it just was from all these things. It was too hard. So that's my little lecture. You asked me, what was a gravitational wave? I told you a little history of why people didn't think it was worth the trouble. Okay. And only in our epoch, when technology has gotten very much better, could we even think of doing something like this?
It is indeed mind-blowing how stiff is the space and how much energy is required to induce even teeny tiny distortions. I guess at that time, Einstein probably didn't know about the existence of black holes. Otherwise, he would be more optimistic about the gravitational wave detection.
And nowadays, you could ask that question because we know about black holes, but black holes were more than controversial in the time of Einstein's when he invented gravitational waves. It's 1916, 1918. No, people didn't even settle on the idea that black holes could really exist until way after Oppenheimer and Snyder. That's a paper that was written when Oppenheimer was at the University of California and with Snyder, who was a graduate student. And that was before the Second World War, 1938 or 9. And they said, yeah, there have to be black holes. There are solutions like that. But Schwarzschild, the man who actually showed Einstein that something crazy happens in his theory, when you get too much mass in one location, space curls up on itself. The space just curls up. It completely distorts. And then you get an infinity in the length of time, how time transforms. Einstein, nobody believed it. And even here at MIT, where it's a pretty modern place, it was only in the late 70s, 1970s, before people began to realize that X-ray astronomers were seeing things that could probably be explained by being a black hole. But many people here, they resisted the idea. They said that's one of the crazy parts of Einstein's theory. It's got to be nonsense. And so when you can't refer to black holes as something that's playing a role in this until about 1970. And then people began to realize just what you have realized, that black holes would probably be a wonderful source for gravitational waves. And why was that? Because they wouldn't come apart. In other words, your two black holes, when they get together, they don't do it, they don't tidally distort. They just get together, they make a new black hole, and much of the energy that they have in them goes out as gravitational waves. That, in fact, is the first source that we discovered.
Since we touched the topic of gravitational wave sources, I'm curious, how do they affect the gravitational wave frequency?
Well, the frequency just depends on, you could do the calculation for a black hole by almost Newtonian calculations, almost up to the point where the two black holes are going maybe 1/10 the velocity of light. But then you have to use Einstein. From then on in, you have to use the whole general relativity because space has so distorted by that time. But you can use just Newton's law. And for example, for the other source that has been detected, which are binary neutron stars. These are stars that are made of real material. They're made of nuclear material, mostly neutrons, a little bit of protons also, a few electrons, but mostly neutrons. And they were discovered, back in the 70s and they are called pulsars because some of them have hot spots on them, plasma spots that make, as the star rotates, it's a very good rotor and it keeps making a very regular period or pulses that come from a hot spot on it. That's a pulsar, but that turns out to be a neutron star. And neutron stars are the mass of the sun, typically, not very much different. They can't be very much. Somewhere between 1 to maybe 2 times the mass of the sun. And when they collide, do some terrible things. What happens is two neutron stars, they get faster and faster. So at the moment when they collide, they're going somewhere, the frequency that you would see if you looked at it with your eyes, the frequency of the motion could be as high as, could be just about 1 kilohertz, for example. These things have been very far apart for centuries. And then they get closer and closer as they lose gravitational energy and they get closer and closer. What happens is they eventually make tidal distortions in each other and then they smash into each other. But just before that, they distribute all their nuclear material all over. And you have a new phase of matter. And that matter is very interesting. It's a quark plasma glue. And that lasts for a few, maybe a fraction of a second. And then that stuff can't support itself and it turns into a black hole. So the other source is the astrophysical sources we have seen are two black holes colliding. And we've seen them all the way from a few solar masses per black hole up to several hundred solar masses, 100 solar masses per black hole. So, and the orbital frequencies that you see at the very end for the heavier black holes are in the hundreds of hertz. And when they're very far apart, they're in the millihertz or milli-years. It probably takes 10 to the 10 years, 10 to the 8 years, between 10 to the 10 to 10 to the 8 years for two black holes that have been far apart who have been bound gravitationally to finally get to the stage where they're so close to each other that they smash into each other and they make a new big black hole. That's what we saw first. We've seen many of those now, and we've seen about 2 or 3 neutron star collisions, which are also very interesting and have made a new field called gravitational wave astronomy.
So when you started off, did you have any bets on what the first object would be that you would observe? Because at that point, wasn't even clear, like not everyone was convinced that there are black holes when you started off with LIGO.
Yeah, the best guess by that time, look, this is now 1917, and there had been a lot of work, and especially in the group of Kip Thorne. We were both young men at Princeton together. I didn't realize that. He was a theorist and I was an experimenter at the time. I was a postdoc and he was a graduate student. And he was already talking to John Wheeler, who became the expert on Einstein's gravitation after Einstein died. He coined the word, this is now Wheeler, who coined the word black hole. And black hole by that time, which is in the end of the 80s, middle 80s, some of very, very good people in gravitation theory saw no way out of a black hole. They saw that there had to be black holes. And that was a big step because the mathematics looks so terrible. Something looks like it's blowing up. There's a singularity. It turns out the singularity is in a place where people didn't realize where it was. It's in a place where quantum theory must eventually have something to do with gravity. And that's one of the wonderful new areas that comes out of discovering black holes like this. You find that quantum theory is going to play a big role in what keeps a black hole from collapsing further and stuff like that. But by the time we made our detection, Kip and his group had already worked out, and so had other people. For example, many of the people who had worked on black hole physics had already figured out what the metric for a black hole would be. And there's a guy named Kerr, and I think he just won the Nobel Prize also for having made the Kerr metric, which was the thing that explained the rotating black hole. And in fact, what we're now finding is that Kerr's metric seems to be right on the money for explaining the waveforms we see. So it's a big advance. And nobody's talking about black holes being crazy. Black holes have become quite central to all of physics. And in fact, I think we're going to have to learn how to explain a black hole with quantum to be able to make progress. And a lot of people think this is a direction that string theory will go. Oh, some people think, I don't know, I don't understand string theory, so I can't promote it. But it's a way that a lot of modern theory is trying to incorporate the idea of the black hole horizon, where everything goes crazy. Time goes to infinity, and the curvature goes infinite, but doesn't really go infinite. It goes infinite inside the black hole, a goodly distance from the event horizon. But all of that is very complicated science, but it has something to do ultimately with, if we ever learn how to do quantum theory of gravity, it'll probably tell us how to do it.
So Rainer, when we look at your earlier research, it's in atomic clocks. How did you come from atomic clocks to general relativity?
I have to tell you, first of all, how did I get to atomic clocks? I flunked out of MIT. I had a love affair, which was very important to me. And that was more important than anything I was doing in school or anything like that. And so I said, the hell with it. I'm not going to. And of course, it was one of these idealized love affairs, which was all one-sided. I was the one who was in love. The young lady was interested, but not really in love. It's a different kind of situation. Happens a lot to young men. And I was prone for that. So I flunked out because I wasn't doing anything. And at MIT, that was pretty rigorous. When you flunked out, you couldn't get back into school unless you had redeemed yourself in some way. And I, as a kid, had done a lot of electronics. And that was my specialty. I was an electronics expert, but not really a very good one. One who knew what I call street electronics. I was able to tell people, yeah, I can build electronics for you. I can even design circuits. And I found a job with a guy named Gerald Zacharias. And if you look him up on the web, you'll find out his big contribution. He was a very first-class scientist, but his contribution in the 50s, in the 1950s, the big contribution was between 1950 and 1957. And then he turned into becoming an educator for the United States and all of science. So he did a good job on that, but let's not get into that. So he was working on atomic clocks at that time. I didn't know it. I just went to a place where there people were working on things that looked interesting. I said, you need somebody to do electronics. And luckily they hired me. So I then became a technician, and I'm union card carrying technician for about 4 or 5 years. And he got me back into being a student. And the way he got me into Einstein, and that's a cute story. He had already made with graduate students and postdocs, but he and I then we're going to make a better atomic clock than had already been made. The best atomic clocks in those days were good to a part of 10 to the 11. In other words, delta F, or delta T divided by T. The uncertainty at the time over a given time was about 10 to the minus 11, which is damn good. The Earth was no better than 10 to the minus 8. So it made tremendous difference. You could measure all sorts of things directly in time and frequency. And it changed all of physics, the way you do physics, spectroscopy especially. You now do it in terms of atomic frequency. So he had done this great thing, and he told me something which I didn't have any idea. He says, this guy Einstein has a prediction. If you take one of these atomic clocks and stick it in the valley next to a big mountain, and you would find that the clock that's in the valley is going more slowly than the clock that's on the mountain. And I said, really? Why? He said, I can't explain that to you, but that's what it says. So let's do that experiment. And so we tried to build a much better clock. We had to build a clock that was about 10 to 1,000 times more accurate. And it turned out the idea was not good, and we never did the experiment. And shortly after that, people with the Mossbauer effect, which is a very tricky, fancy spectroscopy experiment, which has the sensitivity right away, did measure that. They measured the Einstein redshift. But that's how I got into it. And that left me with a permanent interest in Einstein. And fact, from then on in, all I wanted to do was, what did that man do? He was really absolutely spectacular.
So you had ideas for measuring the redshift even before the Pound-Repka experiments down the street. That is fantastic.
A lot of people, astronomers thought they were doing, but it was really reliably measured it was only measured in accurately by humanity. It was accurately measured by a rocket experiment. That did exactly that. They put a hydrogen maser on a rocket, and it flew, and they compared the hydrogen maser oscillations with the oscillations of another hydrogen maser on the ground. And that was how it was put to a part in 10 to the 14th. And then it's been measured, probably no better than that. That's probably the best that's been measured.
Professor Weiss, as I understand, during your youth in the 50s, 60s, a lot of big scientific advances happened. The invention of high-precision atomic clocks, as well as laser, integrated circuits. Also in the same decade, Joseph Weber kickstarted the measurements of gravitational waves. Could you tell us more about that story?
Yeah, that would have been the next little chapter I would have told you but I will now tell you since you asked about it. Joe Weber you have to know something important about general theory of relativity and the way it progressed in science. It was very interesting. And one good example of it is, I think it was the same all over the world. When Einstein developed general relativity, let's say from 1913 to about 1918, and he probably then did cosmology and did all sorts of interesting things with it. But it eventually became so complicated and so devoid of experiment that it became part of mathematics and dropped out of physics. That's what happened. And so by the middle of the 20s, everybody had done the few experiments that you could measure the perihelion advance of Mercury better. People tried to measure the redshift, but they couldn't do it well. And those were the two big Einstein additions to gravity. And the important one at start, the one that was really profoundly important in getting general relativity accepted, was, I think, an experiment which I don't think was right. And that was Eddington's experiment, where Eddington was the leader of this experiment to show that starlight got bent by the sun. That was the big thing that made Einstein famous. And that happened about 1919. And there were a lot of political reasons for that, why it did. It was still the Second World War. The First World War was still going, or was just about over. And Eddington, who was a pacifist and a Quaker, I believe, wanted to show that scientists could overcome these terrible things that are grudges held by nations. And so he wanted to show that an Englishman could do a German theorist experiment and prove the physics. And it didn't matter whether there were Germans or English people in it. It was everybody's business. Okay, he had more to it. So there was a little politics in his head about it. But all right, give it that he might have measured the bending of light. So what came of it is that was about the last thing. And people tried doing that over, and they got more and more crazy answers. I won't go into all that. It's a lovely history written in a book called The Annals of Astronomy. If you're interested in this, look at it by Kluber, Kluber, of all the different eclipse expeditions that were done by people all over the world. And they got less and less good results each time they did it for the bending of light. The real bending of light was finally measured in our epoch by radio astronomy, using quasars and not using eclipses.
Sorry, I have a question. So are you saying that the 1919 experiment was actually not necessarily correct?
Yes, I'm saying it was suspicious. And if you look at it, there's no error budget that really is real. It's not, nobody nowadays would publish that, get it published the way it was published. Okay. On the other hand, there has been a guy named Kennefic, who is a historian of science, who's one of Kip's students. His wife and he looked very carefully at the data from the Eddington exposition, and they wrote a whole book that Eddington actually did manage to measure. But it's something where you have to use there's no error budget that you would believe. There's nothing that you have to go look at the data yourself, reanalyze it yourself. And yes, he probably measured it. And why they say it was because a particularly close, compact group of stars close to the sun. They were very lucky. But nobody, but 20 years after that, measured the bending of light by much better techniques and other. Okay, so the way it was finally done was with radio astronomy, as far as I'm concerned. It's good to a part 10 to the 4, maybe. But now, why am I bringing up all this old history? Because you're asking me a question of Mr. George Weber. Joe Weber and a lot of other people were at a conference in 1957, which was held at the University of North Carolina in Chapel Hill. It's called the Chapel Hill Conference, which was sponsored by the United States Air Force of all people. And where it was for the first time, experimenters and all these people who did mathematical physics got together and said, what should we believe from general relativity? What is the things that are the future for general relativity, and what things are dubious? What things can you believe without having to do an experiment? And they came to the conclusion that the gravitational waves is one of the things. And Joe Weber had a very interesting idea for doing it. And he and Wheeler actually worked on this idea together. And the idea was to measure these stretches in space in a different way. The way I described it to you, it was stretches in space. What is what a gravitational wave is. And in this very slippery theory of general relativity, it is a slippery theory. It's a theory that if you're not careful, then you can reinterpret. You don't have to think of it geometrically. You can think of it as a force. You can think of gravitational waves making a force. It's a perfectly legitimate way to do it. I don't happen to like it. That's why I didn't use that. But Weber were thinking that way. They were thinking that there was a tidal force. That's a force, that's differential force between two objects when a gravitational wave passes between them. And that force causes the strain. Okay? Perfectly legitimate thing. As long as the force is proportional to the mass, there's no way of separating the two ways of looking at it. Okay? And so that's the way these guys thought about it. And Weber then invented, because he thought that way, a technique using a big aluminum bar, a thing that's bigger than a human, probably, maybe 2 meters long and maybe 1 meter in diameter. And he mounted little strain gauges, little things that measured the stretching of the bar on it. And he put that in a vacuum system. And that was a very clever idea. And to his misfortune, he began to see something. In fact, he began to see, and he had 3 of these detectors. One in the University of Maryland, where his office was. Another one in a golf course, not too far from the university, about 8 miles away from the university. And finally, one in Chicago, that's the middle of the United States, in an Argonne lab, in a staircase of Argonne Laboratory. And when he would, these bars, as they would call Weber bars, resonated at about 1 kilohertz to 1.6 kilohertz. So he was looking for gravitational waves at this high frequency, 1 to 1.6 kilohertz. And what he was looking for was an excitation that stretched the bar and then passed through it, and it kept ringing after the wave had gone by. It's like you hitting it with a bell, with a hammer. That's what the gravitational wave is. It's a pulse, it hits it with a hammer, and it sings after. A very clever idea. And what happened to him was that he saw about 3 events a day in all of those 3 bar detectors. And they were about simultaneous. In other words,
a train passing or something?
What? No, it wasn't as simple as that. What happened is, by that time, and this was about all through the 60s, he was doing this experiment. And in 1969, he's so convinced of these things because it was going on for a certain while that he published a paper in Physical Review Letters, which said he had discovered gravitational waves. And he then, about half a year later, said, look, I think they're coming from the center of the galaxy. And there's a little bit of directionality in a bar. It stretches best when the perpendicular to the longitude is pointing to, perpendicular to the bar's length is pointing toward the galaxy's center. And he thought he saw that effect. First, he had it as a 1 bump in his spectrum. Then he had it as 2 bumps, 12 hours apart. And that has always given people the willies. Why didn't he see the 2 bumps right away? But anyway, and then because of that, and that's the lovely part of physics and doing science, it's not such a hard experiment to do. Making a big bar, putting it in a vacuum system costs a little money, but not outrageous amounts of money. But it isn't terribly hard. There were 5 other groups in the United States, 2 groups in Japan, 3 groups in Europe that all immediately started doing the experiment, and no one, any.
What would you say was the historical role of the, wrong Weber results? Did it inspire other people to take these experiments to find gravitational waves more seriously, or was it detrimental to the effort because he said, we had already done this?
No, you ask a very good question. You're asking about the political situation. That resulted by Weber not being confirmed by others. It's a very tricky, hard question. But it was very clear to everybody that Weber had a good idea. Okay? what he was seeing was, and when people started analyzing what he was seeing, they said, oh my God, to get that much energy into the wave, to make that bar, you have to eliminate all the mass in our galaxy in 1 million years. In other words, all the mass in our whole galaxy had to be converted into gravitational waves in 1 million years. This can't be right. We know the galaxy's older than that. It's at least 10 to the 11 years. We now know that's 14 gigayears. So it's a 10, they knew it was 10 to 10 years old. So that was clearly not possible. But he didn't explain what he saw.
Just to clarify, so the actual approach actually could work, but it just doesn't work because the numbers don't work out. But it doesn't have some fundamental physical reason that it fails.
There is no fundamental physical reason that it should fail. And what happened is where the people split. And what happened is where it went bad when Weber wouldn't accept the results of all the other people. That's when it went bad. And he defended his results in Physics and Society meeting. I went to several of them. It was painful to watch. Here is some very good experimenters saying, we didn't see anything. And then Weber would say, you didn't do it my way. And that's not a defense in science. If you can show you have a sensitivity, and it is a somewhat different way of doing it, that should be equivalent. All you have to do is show you have the sensitivity.
And I guess my question would be then, did that then inspire people to come up with different approaches? So of course, one of them was yours, the interferometer, but were there a bunch of other approaches that people considered?
Yes. The first thing that people did is when they saw how much could they improve a bar. And the very first thing people realized, and Weber knew this too, by the way, Weber was not a fool, by the way. He got deluded somewhere. I have a feeling I know what he was seeing, but he never would give me the time of day to explain it. I thought he was seeing magnetic pulses that were pushing on the bar from just thunderstorms. And they exist. You need only 10 to the minus 3 Gauss lasting for a millisecond to make his pulses in a big aluminum bar. Okay? And that looks certainly plausible by what I measured on magnetometers and stuff like that. But he just wouldn't even listen to me. He said, that's just nonsense. You don't think I can separate a magnetic pulse from a gravitational wave? You have your head up your ass, that kind of thing. Okay. The thing was that, and I was too young. But no, what happened is
how old were you at this time?
Let's see, this all was going on 69, 70. So I was born 32. I'm 38, something like that. 38. I'd never published a damn thing about this. I was not really in that business yet. But then later on, we became friends, it turns out. And I began to see what might have been the trouble with Joe. Joe was very easy to get convinced of something if it was something he had done. It was very hard to convince him that something somebody else did was worth. That's how he got into trouble.
What were some of the other approaches that people...
The first approaches was to say, what's holding the bar back? Let me give you the number. I'll give you a number, which stops everything, by the way. We measured, the first gravitational waves we measured with LIGO had a strain of 10 to the minus 21. The best he could have done in his detectors, as they were, was a strain of 10 to the minus 16. 5 orders of magnitude in amplitude, 10 orders of magnitude in energy. Okay. So he was way insensitive not sensitive enough. People didn't know completely, but it began, a lot of people, clever people began to realize the only thing you can do is make the bar more sensitive. They did. They found out what was holding the bar back was thermal noise. The idea that Brownian motion was moving the bar. Just the fact that the thing was at room temperature. So the very first thing a lot of people did, they got the money for it. They cooled the bar to below liquid helium temperature. And people did that for dot sensitivities that were 10 to minus 18. Yeah, about 10 to minus 19. Between 10 to minus 18, call it 10 to minus 19. And what they had done is they made a factor of 1,000 improvement in amplitude over Weber. And they still didn't see anything. And that then was a crucial moment for a lot of people.
Yeah, I'm just interested actually. So the bar was set higher because they could not achieve it. Joe Weber could not achieve it. So how did that make you feel actually? Were you excited, motivated? Were you maybe hopeless?
I didn't believe in the bar. And that's a complicated story. I had that wrong. At the time, I just didn't believe in bars because I didn't like the mechanical approach. I had just learned general relativity for myself with an arduous effort to try to teach it, which was, I think, in some regards, the thing that made me think of when I thought of the better way. But others had already thought of that too. But let me finish with the numbers. At that crucial moment when people got cold bars running and they still didn't see anything, it didn't look possible to make bars better that way. And many people dropped out of the business. Many of the people who had tried to show Weber right or wrong did try to make cold bars. And they got down to 10 to the minus 18 and still didn't see anything. And that caused them to do other kinds of physics. Now, the interferometry has a complicated history of its own. And that is the interferometry had been suggested by Weber himself. I didn't know that, but Weber had said to a guy named Bob Forward, who was one of his graduate students, who had gotten a job at the Hughes Aircraft Company in California and had a little bit of, when he got the job there, he would give him not only the job to develop something for the company that they could sell, he was also given a little time off so he could work on better gravitational wave detectors. And he decided he was going to try to make an interferometer. I was starting on that myself. And the way that happened is that when I tried to explain, I didn't know anything of this. It was all, in my case, I was asked to teach this graduate course at MIT on general relativity. I should have said no because I didn't know any general relativity, but it was very hard for me to say that. After they had hired me and I'm doing experiments on general relativity, I couldn't really admit that I didn't know the theory at all, but I didn't. Now I can admit it now, I could admit it. And I admitted it right after. But so I spent the summer learning general relativity. And there were no good books in those days for that. But I learned it as a geometric theory. And I said to myself, here I can explain how you really make a gravitational wave measure. Very simple. And it came up in a question in the course. And the LIGO in my life came as a result of students asking me, how does a Weber bar work? And I had to say, I don't know really how they work. But here's another way to think about making a device that will work. And that was this was about 1965, 66. I said, why don't you take a mass, stick it out in space, put it over on the left, and get another mass and put it on the right, and make the separation between them pretty big, and put a laser on one of the masses, the one on the left, and put a mirror on the one on the right. And now what you do is you have a little switch. You can turn the laser on very fast, turn on, and that pulse of light goes from the left to the right and then is reflected by the mirror. It comes back to the place where it was started, and there a detector sees it, and then you measure that time very carefully. And that's a way to measure distance, okay? And now what you do is you wait around, keep doing that, and if the gravitational wave comes along and stretches space, it'll take a little longer. And then it stretches it one way or shrinks it. It'll take a little shorter. And you can measure that time. Now, that's a completely fictional experiment. It's like a Godwin experiment. But it explained exactly with very simple mathematics how you could measure a gravitational wave. There was no forces. There was nothing, no magic, nothing involved. And later on, when Weber did not see anything, I thought about it for a while. And I spent 3 months trying to figure out, could you make that into a real experiment? And in the summer of 71, and 72, mostly 71 and partly in 72, I came up with a way that I looked at all the noise terms that such a system would have, but you would have to immediately make it into an L. You have to have two distances to separate so you can measure their difference. But then you look at all the noises, and I did an analysis of that, which looks to me that you could measure something of the order of 10 to the minus 21.
So Rainer, we actually put a napkin right in front of you in preparation for today's fireside chat. We actually did a back of the envelope calculation, or rather front of the napkin in this case. Does that capture the main essence of noise, or in this case, the limiting factor being shot noise? Does that capture in our short calculation?
That captures part of it. The noises that are actually limiting us now. In the early days, it was shot noise. That's quantum noise, but it's only one part of quantum. See, quantum, that initial paper I wrote in 1971 or two, it looks at all the noise terms. It turns out that, yes, this is a big term, but there are far bigger terms. Until you get rid of those, this is still unimportant. And now and the biggest term was thermal noise, even in that. Then the next biggest term was seismic noise. How would they get rid of that seismic noise? Just the fact that you're on the earth, which is shaking so. That was very hard. And that took us almost 6 years to really get rid of. And then when you get rid of the seismic noise and thermal noise, you finally get to the level of the quantum noise. And there are two versions there are two pieces of the quantum noise. What you have calculated here is the shot noise. It's perfectly right calculation you made. And to do that, you win there by having more power. Because in square root of the power, whatever the square root of power. But the other, as soon as you increase the power, you increase another problem, which is just as bad. The photons that are in the beam push the mass around, fluctuations. And those are the vacuum fluctuations of the electromagnetic field. And those you have to control also. And that's where squeezing comes in. And now that's become a very big deal. The idea of adjusting the momentum noise that comes with the light. And then you have a new thing, which is the quantum noise, which does limit us now. So your calculation is half of the quantum noise. The other half is the radiation pressure fluctuation. And you can make them, if you're tricky, that's where the new quantum theory of nothing new in this, but the squeezing, getting states. Let me say it another way. You can tailor the way the vacuum fluctuations affect the measurement. See, what makes the 1/2 h bar omega that's in each mode of the radiation field is the vacuum fluctuation. There are fluctuations in the electric fields. There are no average values in the electric, but there are fluctuations in those fields. And those fluctuations can be promoted into real fluctuations when they interact with a real electric. So if you have a cross product between a laser field and a vacuum fluctuating field, you can get radiation pressure noise that is due to the vacuum fluctuation. And you do that. It's a very simple calculation. Try it for yourself. You have to square the total field on the matter. Okay?
We will do that and post that as another napkin.
Yeah.
That's our homework.
Okay.
Okay, interesting. We also have someone from our audience who has a question for you. So maybe I'll just introduce you to Soham Sah. He's from Purdue University and he's currently doing there also a postdoc. Go ahead.
Okay, this is a bit of a personal question. Yeah, at the beginning of the discussion, you mentioned a little bit about a very interesting love story that led you to leave MIT, and I was very curious about how it ended. If you don't mind.
It ended badly. For me, it ended badly because it caused me to flunk out. But then, about 50 years later, we got to meet again, and that turned out quite well.
Well, yeah, man, that's very interesting.
That's very inspiring. By the way, this is an announcement also to all the participants. Since you have this unique opportunity to directly ask Professor Weiss a question, so don't hesitate and give us a sign that you would like to ask a question and we'll enable your microphone.
If you could build cost is no object, and you could build any physics experiment you want in space or on Earth, what would that be?
And look, you'll think I have a very limited imagination. The thing I would love to learn about, and something that none of the experiments that are now going on can touch, is I would love to find out, is there really a cosmic background of gravitational waves that is not from sources in our astronomical, like black holes or neutron stars, but rather is actually due to what went on at the very earliest moments. In other words, let me give you a little feeling about that. And by the way, LIGO can't do this. LISA, which is the space version of a gravitation detector that we'd be flying in the 30s, can't really do this either. You will have to build something very special. It has a name, and it's something that's already put on the web. It's called Big Bang Observer. That's the name of the project. And what the idea of this is to actually try to measure the vacuum fluctuations that caused the universe to expand. In other words, the idea of inflation, which is an idea that now seems to work for many of the ideas in cosmology, that the universe had a moment in the history, very early in the history of the universe. The universe expanded so fast that it went from something which was nothing more than a peak, a little vacuum fluctuation, to being a full-fledged universe, which is maybe the size of a grapefruit, or maybe even on Earth. I don't know. I don't know the size, but the expansion of the universe took place with 20 orders of magnitude in sort of 10 to the minus 20 seconds. That's inflation. I don't have those numbers right, but it's an instant where the universe went completely crazy. And there's a new field. There's something called the inflationary field. And why do we believe in this? There are many reasons. And if you want to learn about it, look up some of the papers by Alan Guth. And he invented this idea a while ago. It explains an awful lot of what we now know about the universe. And one of the things that he didn't know, Alan didn't know at the time when he invented it, it also generates, this is the work of Starobinsky in Russia, that it also invented primordial gravitational waves from the quantum fluctuation that took place during that time. The accelerations were so huge that during that time, the whole universe got filled with gravitation. And they are very much like the cosmic background of electromagnetic waves. They're not thermal. They're not thermal. They don't have a temperature, but they have a background. And it turns out that they are, with the current estimates that Starobinsky has, they are about 10 to the minus 13 in energy density, the amount of energy per unit volume of the universe. They are about 10 to the minus 13 of closure density. In other words, and we can just about do 10 to the minus 7 or 10 to the minus 8 of closure density for stochastic background noise of gravitational waves with the apparatuses we have now. So we would have to have a factor of 10 to the 5 improvement over where we are now. And we're not going to get that from LISA, and we're not going to do that on the ground. So what is this? What it is, it's a space experiment, which mixes the two technology. It takes the very, very precise technology of position measurement that we do on the ground, which is 10 to the minus 18 meters per square root of bandwidth. Positionally, 1,000th the size of a nucleus. We can measure the size of 1,000th the size of a nucleus. And it takes that and puts it into space where the pathways can be thousands of kilometers. Okay? And then that gets you to the domain where if you have some constellations of satellites, like a hexagonal constellation of satellites, in an Earth orbit, or in an orbit that is that's 1,000 kilometers across, so that's smaller than an Earth orbit, you could probably get the sensitivity to measure the cosmological gravitational wave background. And why is that the most important thing to do? It takes you back to the instant when the universe got created. I can't think of a much more interesting problem. The moment when it happened, 300,000 years after the universe, which is now, whereby there are experiments going on right now trying to measure the polarization of the cosmic background, the electromagnetic background. And people at Harvard are trying to do this. People all over the country are trying to do this, also in Europe. And what they are hoping to see is the polarization change. Here are, at the time when the universe became transparent enough so you could see the cosmic background, there are clouds of plasma. And these plasma clouds have been pulled and stretched by those primordial gravitational waves so that you can get polarizations that have a very specific pattern of the cosmic background radiation. And that's what people are trying to measure right now. They thought they had measured it 3 years ago, but they hadn't. They had measured dust polarization.
Bicep.
Bicep, exactly. No, but there are now people really trying to do this from the ground. They're hoping to get the ratio of the tensor polarization to the scalar polarization of about 10 to the minus 2. That's what they're hoping. And the predictions are you have to get to 10 to the minus 3 or smaller in order to be done. So really there probably isn't I hope they see something. That'd be wonderful. But and it'll tell us what the energy is of that inflaton. That's what it will tell us. Now, there are other things that maybe come from the primordial universe, which also, but these are not as well established. Every time the universe goes through a phase transition, for example, give you an example. When the gravity separated from all the other forces, that's a little bit after this inflationary period. See, during the inflationary period, gravity was repulsive. It had to turn itself around and become attractive. So that's what happened. And at that juncture, there's a good bit later in the universe, there may be bubbles where the thing didn't happen exactly at the same moment. And that could cause gravitational waves that you can see. That could be seen maybe by LISA. And if it was even later than that, when the electromagnetic forces separated from the weak interact, that's even later still. That could be seen by improvements in ground-based LIGO, for example. But neither of those is as deep a problem as looking at the very earliest motion, actually looking at the spectrum of primordial gravitational waves that will tell you what happened at time t equals 0 plus infinitesimal 1. To me, that's the most fascinating thing I could.
Absolutely fascinating.
But it's not going to happen for a while. You have to do two complicated things. You have to put LIGO into space. And by the way, the LISA, by the way, will have a position sensitivity of only 10 to the minus 12 or meters per root hertz. On the ground, LIGO has 10 to the minus 18 meters per square root hertz. So you need a factor of 1,000,000 improvement in the position sensitivity of LISA to do that. And that, unfortunately, because the way LISA does its position measurement, it can't. You have to do something like what we do on the ground, where we actually use high power light and we lock the fringe so that we can look at it very carefully. In LISA, what's seen is a heterodyne fringe. And that's a completely different thing. They can get away with 1,000,000 times less sensitivity and get to 10 to the minus 21. See? So that's the experiment I would love to see people think about. And I will be long gone when it happens, but I hope somebody actually carries forward that.
Yeah, that's really interesting to hear. Yeah, so just probably there's a lot of interest in hearing more about LIGO. So I think we have a couple of questions about LIGO. Maybe Xinhui can ask the first one.
Yeah, one of the questions is when you applied for funding with the NSF or proposed, this is such a difficult, insane proposal. How did you get the NSF to fund what at that point was the most expensive project they would be funding?
No, it's not the most expensive project. Very most expensive project that they funded was something that was a total failure. Now the political thing, let's not go into that. But you're right. It was a very tricky problem, getting LIGO accepted by the scientific community. And let me tell you the secret. There is a secret. There was a man whose name is Richard Isaacson. Okay, Richard Isaacson, who was the head of gravity at the NSF, the discipline of gravity. And he was an expert on gravitational waves. And he showed in his PhD thesis that gravitational waves actually carried energy and momentum away from their source. He actually showed it. And that stopped all the arguments. Okay? So he had an interest in gravitational waves. He took a position at the NSF. And he saw that if he could talk to the people at the NSF, his boss and his colleagues, that there would be an interest in gravitational wave research. And now here was the miracle that he pulled. The miracle that he pulled is at the time when we made the proposal for LIGO, we did it. We had some advances in the technology. We had some advances in the sources. We knew a little that maybe black holes really could exist. We began to think very hard about neutron star as possible source. So it was no longer just supernova, which was it. But we didn't yet have demonstrated the sensitivity. We hadn't demonstrated that yet. So what he did is he guided us through the whole process of how to present the case in a way so that it would get through the system. Now, not that we didn't know enough, but he really told us the right way to do it. That's a little bit of a cheat, but he then, as we went through different crises, and we went from all sorts of crises, people not believing us, the astronomers saying this is a waste of money, the Congress not wanting it, the people on the National Science Board saying, no, this is too complicated. There's no payoff here. That's soon enough. All these different arguments. He helped. Every time we had arguments like that, he helped in getting us organized in such a way that we made the right arguments in front of the right people. Okay? And he retired shortly before the discovery. But all through that epoch, he was at the NSF and kept us alive by being rational, making very elegant arguments to his to people around him. He was the guy. As far as I'm concerned, without Rich Isaacson, we would have never made it. Okay? Now you can, what? And that comes straight from my heart. I'm sorry. There's no way around Isaacson. Rich, what did Kip Thorne and I do? We made a physics prize, American Physics Society prize, in his name. And it's for people who are in this very difficult field of relativistic gravitation, who are doing interesting stuff. They can win a physics prize every year. It's given. So Isaacson live on for as long as there's an APS.
Yeah, well deserved.
Yeah, for us, he was well deserved. And I don't think anybody hates us anymore. They were very angry with us because they thought we were just wasting all this money.
That's really interesting. It kind of suggests if someone's listening that is in a similar position to where Isaacson was, back in the day, that actually you can make a very big difference as an individual.
Absolutely.
And that's both inspiring and also a lot of responsibility for people who take on these roles, right? Because if he hadn't done that, maybe LIGO wouldn't have happened.
I certainly wouldn't have.
Yeah, I think follow-up question on that is, if you look at all the different engineering solutions that went into LIGO and all the kind of tricks and great ideas that got it to work, what is the one that you're most proud of or you think is the most interesting story in terms of just straight engineering solutions that went into LIGO?
You'll laugh at this. Everybody thinks that the position sensitivity that we got, the ability to measure 10 to the minus 18 meters. And yes, that's an accomplishment, no doubt. But once you analyze the instrument and you go along, you can do that, it turns out. And I think now we can go further because of the understanding of the quantum noise. I was involved in something which was very much ordinary, but could have failed, and it didn't. And that was one of the things we knew we had to do. And in order to make 4 kilometers of vacuum, 4 kilometers vacuum at, call it 10 to the minus 9 torr, or even 10 to the minus 10 torr, at what is called ultra high vacuum. I thought that was an engineering task that we took on, and we won a big gamble. A lot of people thought we would never be able to do it at the cost that we did. And the same thing is going to happen now with the next version of LIGO, which is we hope to make longer. We hope to make a 40 kilometer long LIGO arms in the next version, because we now know what sensitivity you really need. Having measured all these sources, we know we didn't make LIGO long enough. If we want to get into cosmology, near-term cosmology, for example, where did all those black holes come from? Or what star, were there primordial black holes? Did they all have to come from the stars? These are now profound new questions that have arisen. Or what was the first stars that were made? What were they made of? We think they were made of hydrogen. They most certainly were made of hydrogen, but how long did it take for the very first stars to form? And that's something that James Webb will tell a little about, that new telescope. Anyway, these questions can be answered also by gravitational wave research if we make this thing 10 times more sensitive. I don't think there's any point in making it more than that sensitive on the ground. But that extra factor of 10 will get us into what I would call the beginnings of it's the end of the early moment of the universe and the beginning of what's really astronomy. It takes us to a mega year after the explosion. The cosmic background takes you to about 300,000 years after the explosion. This will take us to about and unless it's stronger sources still. That's something we're pushing in the United States. It's called Cosmic Explorer. And that, of course, is the next thing, and I think it's a very realistic thing. And that has the same problem. How do you make the vacuum system cheaper so that you can afford it? And for LIGO, what that did is we made something that which, of course, normally would have cost, it cost about $50 million. And with all the innovations we made, it would have cost 6 times that, $300 million. It would have completely wiped out the product if we hadn't learned how to make a cheaper vacuum system. That was an engineering challenge. You asked for an engineering challenge. That was it. There were a lot of tricks involved. The most important one is that you could learn how to get rid of all the things that made gas by doing cheaper things. You could bake hydrogen out of the steel. You could, with a low temperature bake, could get rid of the water. And so consequently, you didn't have to pump. You had a very big diameter, very different. See, an accelerator is like this. And you have to have many pumps. We were able to get away because we thought it through carefully, that we had only pumps at the ends of 4 kilometers. Okay. We designed the thing in case we were wrong for pumps every 250 meters, but we never had to buy them. Thing we just, a lot of sort of very ordinary calculations showed us that if we could save probably a factor of 3-4 on the vacuum system.
I can imagine like the whole team must be working on that. From our audience, we have another question coming up from Brian. Would you like to ask your question?
Yes. Hi, Ray. It's Brian Keating from UC San Diego. How are you?
Huge.
Good. Thanks for coming on the podcast last year. I made your conversation as part of a book, and I'm going to send you a copy of the book. You and Barry are in it. And
they got Barry. The hell with me. Barry's a book.
Barry wrote the foreword to it. I'm very impressed. Next edition, you'll write the foreword to it. I want to ask two questions. One is about there's a very kind of wild proposal, maybe not even a proposal, but a proposal to make a proposal to put a collider on the moon because you can do a lot without building a vacuum system pertinent to what you were just saying. So that's one question. And do you think that's feasible for an advanced futuristic version, maybe in the next century? And then the other question has to do with GR and the existence of artificial intelligent physicists. And the question is as follows. So Einstein is called the happiest moment of his life, that if you were in free fall, you would experience no gravitational force. And so the equivalence principle, he called that the happiest moment of his life. And people are talking about making an artificial Einstein, using computers, advancing technology to have an artificial intelligent physicist who's even better than Einstein. Your colleague, Max Tegmark at MIT, for example. I want to ask you, do you think that's possible given the fact that how does a computer experience happiness? And how could a computer reason what free fall would feel like, quote unquote? So are you optimistic about artificially intelligent physicists making breakthroughs like Einstein? And can we put a LIGO version on the moon? Thanks very much.
Those are wild questions. My God. Look, I've never thought of an accelerator on the moon. I've thought of, but it's not as flat as you think. Okay. That's one of the problems. And it's not as quiet as you think, the moon. But for gravitational wave, people doing the same thing with gravitational waves, putting them on the moon. And it turns out that that would be interesting. You have to get around the moonquakes. They are moonquakes that come from thermal expansion. Accelerator would be troubled by that so much, but I think if you're careful enough, you need an awful lot of other things than just a vacuum to make an accelerator work. You need magnets, you need lenses, you need a lot of stuff. I don't know, has somebody actually calculated whether it's I guess the number that I would have to make if I was going to answer that question reasonably is what's the cost per pound to get stuff up to the moon? And if you talk to people like Werner von Braun back from another century, he'd tell you, oh, it's $1 a pound, which is complete crap. But what is a real number for that? And then you could sit down and say, okay, let's look at the cost of making it on the ground and on the moon. Right now, I think the moon is politically interesting only because the United States is worried about China taking it over. And that's why you might have people listen to you. But I can't answer your question without having done some of that thinking.
The only thing I can think, Ray, is that you wouldn't have guys with shotguns going hunting and shooting the two.
Yeah, you're right. That is certainly what eventually there'll be some people there who will be nasty too. Look, I can't answer that question, but it's very clear how you answer it. I think it's an economic question. The thing about the computer is much harder. My guess is, and this is can you get a computer to have an orgasm, for example? I think it's the same kind of question. And the thing is that, yes, I don't know what it feels like, but it could go crazy. My instinct says that Einstein didn't mean that it was a physical feeling in his whole body. I think he felt emancipated from an idea. That idea now is practical. It wasn't that if you're trying to make the computer feel like Einstein did for having made the discovery, you have to define what makes a computer happy. But you're not asking that. You're asking, can you make a computer have an orgasm that's equivalent to or something like that that's equivalent to what a man or a woman has? And I don't know that. I don't know what it means. So I'm not really answering your question. I'm sorry. The more I think about it, the less I can answer.
I have another question in mind. You're talking a lot about the Duncan experiments and so on, about different people, also such as Einstein and everything. And right now we have this thing coming up of the metaverse and virtual reality and all those kind of things. Do you imagine people doing Gedanken experiments maybe in virtual reality or something? Or what do you think that can enable people?
You're talking about the meta materials that you told me about earlier?
No, like more the kind of, so Gedanken experiments as you were talking about.
Oh, Gedanken experiments. Okay. And what about them?
And then right now we only do them in our heads. So we're now only doing them in our own head or something and stuff like that. And sometimes when we get stuck, we try to make a drawing of it or something else of it. And now we have more interesting opportunities coming up, or this kind of virtual reality where you can put some kind of virtual reality glasses on and stuff like that.
Yeah. Okay. Now I think I understand what you're asking. And I think like the Gedanken experiment is another word for innovation. That's the closest I can come. And I think a lot of people, for example, the head of the NSF now is a guy who is very much interested in the idea that everybody, if they once understood a problem, they would innovate properly. And I don't know, it's something one should think about. And everybody, and effectively every person in the world, once they understand the problem, will innovate to get a solution. That's, I think, the same kind of question. And he professes that, by the way, and he gives TED Talks that make it sound like that.
Okay. Just quickly, because it's been bothering me since you said it. So you mentioned that you made the tube a lot wider for the LIGO than a typical accelerator. Did that improve the vacuum because the off-gassing comes from the walls, but the total volume gets bigger and relative to the surface area?
No, you're very close to the answer. What it is, the pumping speed of a tube, okay, goes like the area divided by the length cube. Okay. So it turns out that if you can make the area very large, you don't have to have as much pumping. You don't have to put as many pumps around the system because the friction effectively, or the scattering by the walls of the molecular flow, is not as much inhibited by the tube if it's a larger diameter. And so, for example, no accelerator could ever live like that, have a pump only once every 2 kilometers. Why? The two reasons. One is they're much smaller tube, and so the resistance in the tubing will keep the pump from working properly. Okay. But the other one is that the accelerator also causes gas. In fact, when the gamma rays hit the wall, they come from the Bremsstrahl from hitting atoms. You get heating of the walls and it makes more gas. So they have a different problem. We have laser beams in there, but they don't hit the wall. They hit the mirrors. Maybe 1 part in a million hits the wall. Okay. And so thereby don't make a source of particles that are outgassing the wall. So there are two reasons. It's better pumping speed and you don't have a source in the back.
That's interesting.
Okay, so there is one more question on the LIGO side. We found there is a statement that LIGO has been claimed to be the most expensive project in NSF's history, at least at the time when they funded it. So it says that almost more than $400 million were budgeted for it at the time, the beginning stage. So that's fascinating. And how did you and your team manage to get that financial support for the project?
The numbers give you the numbers right so that you have them. The whole thing was proposed as at its initial construction of about $280 million. That's what the initial proposal was. And that built all the infrastructure, beam tubes, the buildings, and the detector, initial detector. And then there was another request for about 130 million. I'm not sure of this number, but it could be between 150 to 130 something for the advanced detector, which is the one that ultimately made the detection. So add that to the other part of it, which is about $50 million a year to run LIGO. And that is, when you put that all together, you wind up with a number that's close to $1 billion. And the biggest expense is the running of the LIGO for all those years. And NSF is finding that as a big problem for a lot of their facilities. How do they keep making new facilities which are better, and then the running costs are something that is eating up money that doesn't have a special source of money. Let me say, well, right now, there is something called the Major Research Equipment Facilities Construction account, which is something like $400 million a year. And of that, LIGO was one of the first to use that account. Then all the other NEON, many other projects that they did, ARMA, and even the high energy. There's been a history ever since LIGO did that in 1994 of using that MREFC fund to build new things. But then what happens is as you do that, you keep putting a bigger burden on the continuing money that comes for operations. And that's something that has to be solved. As they get more and more facilities, they really have to shut some down, which are no longer productive. And that's hard because they typically they stay quite productive. But that there is not yet a line item in the NSF budget for operations of these facilities that have been supported and built by MREFC funds. And that, I'm afraid, is something that Congress has to look at seriously because it's going to become more and more of a problem. Did I explain enough? I think that's the best I can tell you. It wasn't all in one shot. That's not the way it was. The MREFC account is what paid for each shot of doing something new. But then the running costs came out of the general NSF budget. And that's what turned out to be.
One question that we all really wanted to ask is, you had obviously a strange career in academia. You left, came back, and so on. And it's amazing that somebody like you can also achieve so much in academia. What's your advice to researchers that are either entering the academia today or just science and engineering, or are closer to like where you were in your late 30s when you got into gravitational waves? What's your advice about how to think, how to approach your research, how to approach dealing with the rest of the scientific community and working with them and so on? Just a general question of like how to view the world.
These questions are getting harder and harder. My attitude has always been that you have to do two things. One of them is you have to convince your colleagues, if they're not already convinced, that this is something they think is interesting. Or they come with you as being interested. You can't do something as a lone individual. That's impossible. If you have a good idea, talk it up at colloquia, talk it up, write papers about it. And very often you will find that there is a group that will condense on that idea. That's the first. There has to be some group that thinks this is worthwhile. And generally, I think that the grander the idea, the more likely is you will collect colleagues. In other words, if the idea is really quite doable, but has a wonderful motive, tells you something about the beginning of the world. And I pick that because that seems to be something everybody's interested in. How did the universe start? It seems to be, my God, if you could find that out, done something amazing. So the idea has to be reasonably interesting to a lot of people. And the other one is that you then want to make sure that you have some good people who can look at the costs of it. Because the very worst thing that you can do is do something which is you think costs X, and by the time you finish costs 10X. That not many people can get away with a thing like that. And I think that's what happened to the SNC in a way. Part of it was in the SSC. That's a book which it has been written. I think people tried to analyze. Rigdon has written, I think, written a book about this. What went wrong there? And it was that there were people backbiting in the scientific community about the cost of the SSC and its necessity. I felt those people were probably wrong. It was always important to keep high energy physics going because it's one of the most interesting areas of physics. On the other hand, you can't just cavalierly say we have to increase the diameter of the beam tube because the magnets have already been designed. Let me say it carefully. There was at the very end of that project a feeling, my God, there was a misdesign in the sides of the beam tube because of charges being emitted by the wall. That was coupled with how strong magnets were. And the people said, or they'd be safer. They had already built many of the magnets, but it would be safer if we made the diameter bigger by a certain number. I don't know what that number was, but the numbers for making the magnets had already been expended. The numbers for making the vacuum system had already been expended. And so they pushed, and that was arrogant. They pushed, they were scared to death that the thing wouldn't work. And they pushed for an increase. I don't remember how big it was, but it was significant. And that's when I think it was Clinton who had to shut the thing down because they were asking, I don't remember the numbers. They were significant. They were billions of dollars increase that came from trying to make those changes. And that, you can't really do that. Yeah, you may have to just live with the compromise. Anyway, look, you asked me what? You asked me how to succeed. I think the other thing is, look, you don't always have a Richard Isaacson. That's the other thing, but if you can. That
Must be, it's be lucky to have him actually there.
Yeah.
We see we have another question coming up from Orat. Orat, Croatia. Would you like to ask your question?
Yeah, hi. My name's Orad. I'm at the University of Ottawa. I'd seen you present at PQE a few years ago, and I thought that was one of the best talks I'd ever seen, just about all the little inventions and stuff that went into getting LIGO to work. So that was pretty cool. So my question is along those lines. It's maybe a bit romantic. You're a bit of an older fellow. You were probably in your 20s, maybe starting research or something like that when the laser was first discovered. So my thought is, what do you remember of that time? The first time you heard of a laser or saw a laser in person or read that there was a laser developed? What did that conjure in you at the time? Do you remember?
Oh yeah, I know. The laser was 62 and I remember being at Princeton, 62. And there were some guys at Princeton who had connections with Bell Labs at the time. And they had I forgot the name of the physics building, but they had ranged a bunch of mirrors that would take the laser beam from the basement up to the top floor and that back down again. And that mirrors that, and the beam only grew with the square root of the length. And it looked like a beam of light was holding together and you could follow it up the stairs and then down again. And it was fascinating to see that light would do that. And of course, what we were looking at was a Gaussian beam. And that was very much in my mind when we began to think of how could you make measurements of long distances. And first thought I had was something very different than gravitational waves. It was something Bob Dickey, who was at that time the guy who was in charge of me. I was a postdoc with Bob. He was thinking very hard of why was it that an idea that Dirac also had, and namely that maybe the large numbers in physics were all somehow tied together. For example, the number of the size of the universe versus the size of the Compton wavelength of an electron, for example.
Yeah, that's pretty notorious, right?
Yeah. And you find out 10 to the 40 is that number. So then you find out that, and then Dirac looked at, my God, if you look at the number of particles in the universe, or at least what he thought was the number of particles in the universe, and looked at the mass of one part, the mass of the particle, that's 10 to the 8. So there's a square of 10 to the 40 involved with that. And so the other one was just the size of the universe must somehow relate to G, because GMRC squared, that quantity, C is probably constant. Radius was determined by how old the universe was. And the G and C and G is supposedly a constant, but maybe not. But if GMRC squared was a constant forever, then G would go with R. And R grows with that size of the universe. So maybe G is changing with time. And that sounded very interesting. And a lot of people thought maybe G would change by a factor of 10 to the 10 per year. And that seduced me into thinking, my God, how could I measure this? And that's where the laser became very important. Because one of the big problems you have to know is how much does the Earth change dimension? And I thought you could do that with lasers, strand fields in the Earth. And you could measure the mass of the Earth by making with a very good gravimeter and see we were using it tied to an atomic clock. That was really the very first project I wanted to do when I came to MIT as a young man. It was completely fanciful. And they let me get away with it for a while, but it eventually reality hit. Okay.
Yeah, thank you for that. That's really fascinating.
So we're starting to run out of time here. We have one wrap-up question. And this is kind of a strange one, but it's interesting because you've mentioned the beginning of the universe several times. Do you think that the existence of the universe, it's just the fact that we're sitting here, that all of this around us and that it exists at all, can be explained without invoking something irrational? So like a God or something at the beginning or whatever, however you want to call it. But is there a self-consistent way that we'll find someday to completely explain it without invoking some irrational or something at the beginning?
Well, that's again a hard question. And Brian Keating started with this hard question. They're getting worse and worse. I have my own opinions about this. I hope in the end, we can come up with rational understandings of nature. Okay. And now nature doesn't mean that I can understand why does music make me feel like I'm ready to jump up and down or I'm ready to cry. I know that music affects people in a way which I think is almost ethereal. I don't know. Okay. How does that happen? That I don't think I've explained that. And I wonder if you take enough images of the encephalography, images of the brain, you might get to understand this. My own feeling is it's going to be someplace where the problems are so complicated that your understanding isn't going to be good enough. That doesn't mean I prove that there's a God. That's not what in fact, I would be disappointed if it did that. But it would prove that you cannot produce everything into a rational way. I believe that. There are parts of physics I can't understand. String theory, one of them. Or even solid state physics sometimes gets so complicated that I wonder if if it really encompasses everything that we know already and is past what we can handle. Anyway, so I can't answer you any better. I think that the mythology, God, other things, but that God should take a specific interest in me, I would think that's absurd. Why should that be? That's a separate problem. That's an arrogance problem. If there was such a person, it would be very busy with a lot of other problems.
It is the time to wrap up. Let's give special thanks to Professor Weiss for being our guest speaker today. By the way, this is a historical event, the first ever live conversation with a Nobel laureate on Twitter Spaces. I personally learned a lot more about various aspects of the LIGO project and was happy to hear many other interesting stories. Also, thank you, the audience, for your participation. Stay tuned for the upcoming events.